Okay, so welcome back everyone. So in this video, we'll be looking at a quick review of graph theory. So this is by no means meant to be a very comprehensive overview of graph theory. In the theory of computation courses that you might take, you sort of deal with graphs in a very pictorial fashion. So you're drawing a lot of graphs, but you're not necessarily studying properties of graphs or proving, for instance, that there exists an Euler circuit or that there's a Hamiltonian path in your graph. It's just there really as an aid. And so I just want to remind you some of the terminology that's used with graphs, and in case you don't really remember what these mathematical objects look like, I also want to sort of remind you on that. Okay, so first of all, what is a graph? And already there's going to be a distinction between an undirected and a directed graph. So in an undirected graph, you have a collection of points, which are typically called vertices or nodes, connected by lines, which we also call edges. Okay, so in an undirected graph, there is no direction in the edges. Okay, so for instance, in this graph here, GA, so I've drawn a graph GA here. I have my vertices. My vertices are 1, 2, 3, 4, 5, right? And my edges are, let's say, the edge 1, 4, right? So here, there is no direction in the edge, right? So it doesn't seem like if I were to take a walk from 1 to 4, that I would go this way or this way, right? Like there isn't a direction to the edge. There are no arrows. Okay. In a directed graph, so in a directed graph, edges do have arrows to signal direction, and all edges are going to have arrows. So there's such a thing as a graph that has both directed and undirected edges, but we're not going to consider that case. We're just going to consider completely undirected and completely directed graphs. And actually, in theory of computation and in theoretical computer science courses, you typically just deal with directed graphs. But um, knowing that there's sort of this different class of graphs is important. There's two different classes of graphs based on the direction of the edges or the lack of their existence. So in my graph here, GB, I have 4 vertices, 4 nodes, A, B, C, and D, and I have directions to them, right? So let's say there's an edge from C to B, but there is no edge from B to C, right? So what that implies that if I'm at B, I can't actually go to C, right? If you look, there is no path for me to go from B to C, but there is a path for me to go from C to B. And this notion of um, being able to go from one vertex to another, or we're later going to say one state to another state, that's going to be very important when creating these graphs that are going to be related to computation, which we're going to see in a few videos from now. Okay, so that's the definition of a graph. And the next thing I want to point out is how do you sort of formally represent a graph? So what's the mathematical notation typically used to write out a graph? So there's a lot of text here, but I'll just highlight what's really important to know. So for undirected graphs, you can write the graph G as a tuple V comma E, where V is the set of vertices and E is the set of edges. Okay, so actually, if we go back to this example, so I have my graph GA here, right? So GA can actually be written as VA EA, right? Where VA is the set of edges and sorry, VA is a set of vertices and EA is a set of edges. So what that looks like, right, is I have VA. So what are my vertices? I have vertex 1, 2, 3, 4, and 5, right? So it's the set from 1 to 5, right? Those are the labels. Actually, these aren't actually the vertices, right? They're more like the labels of the vertices. And then I have my edges, right? So how do I represent my edges? Because I have an undirected graph here, I'm going to represent the edge. So let's say the edge 1 to 4 here. This is going to be represented as the set 1 comma 4. So why the set? Because remember, in a set, order doesn't matter, right? So 1 comma 4 is the same as 4 comma 1. And that conveys the same thing that an undirected edge is conveying, right? So it doesn't matter. In an undirected edge, you can go from 1 to 4 just as much as you can go from 4 to 1. And so this sort of disregard or non-importance to order is also reflected in a set, right? So to write out formally the edges of a graph in the set E of A, right? So in this set here, I can just write out the list. So here I'm going to have a set of sets, right? So I'm going to have a set of sets where each set represents an edge. So let's say 1, 4 is an edge. So this represents an edge, and namely that set is going to have 2 elements. So edge, and so that's going to be a set of 2 elements, right? So I'm going to have the edge 1, 4. Then I'm also going to have, right, so there's a comma, the edge 1, 2, the edge 2, 3, the edge 3, 4, 1, 5, whoops, 1, 5, and so there's a comma here, and 2, 5. Okay, and just to check, you can just see what's the cardinality of E of A, right? So what's the cardinality of E of A? It's 1, 2, right? It's 1, 2, 3, 4, 5, 5, 6. So it's 6, and then you can just cross-reference that by counting the number of edges in your graph. So there's 1, 2, 3, 4, 5, 6 edges. Okay, so that should be good, right? And so that's how you would write out mathematically and like formally the um, the representation of G of A. And you'll notice that like now that I've written down this mathematical representation, it doesn't really matter if I had just this representation and I didn't see this pictorial representation. If I had written back the pictorial representation, it could have been anything, right? So it's not necessarily going to look like this, right? So all of these graphs are going to be sort of isomorphic, but that's more of a topic for a graph theory course, but it's just to let you know that, you know, once you have this formal representation, it means that um, any pictorial representation is equivalent, right? So it's referring to the same mathematical object. Okay, so that's how you represent formally an undirected graph. For a directed graph, it's very similar. So you have, so if I go here, so you have your set of vertices. So here it's for the graph GB. You have your set of vertices and your set of edges, UB, except that now the set of edges, so for each edge, for each directed, whoops, for each directed edge, each directed edge is a 2-tuple. So, and how this works is that the first, so remember in a tuples are ordered, so it matters if you write A comma B versus B comma A, right? So in tuples, A comma B is not the same as B comma A, right? So what A comma B is saying is that it's saying that you have a vertex A and a vertex B, and the edge is going from A to, that's annoying, from A to B, right? So A is the sort of outgoing, it's the outgoing part of the edge, and B is the incoming part of the edge, okay? So that's why you write these as tuples rather than sets, because um, in directed graphs, you care about the direction of your edge, okay? So that's how you would represent um, a directed and an undirected graph formally. Okay, so now that we sort of know what a graph is and how to define it and how to write it down formally, we also want to talk a little bit about how do you quote unquote walk through a graph. So what I mean by walk through a graph is how do you sort of navigate through the graph as if it were um, a set of streets or a set of countries on a map, right? So how are you able to navigate through this graph? And what are the different ways of doing so, and what are each ways called? What is each way of navigating through it called? So the very first way of navigating through a graph, so it can either be directed or undirected, is known as a walk. So a walk from V sub I1 to V sub IN is just a sequence of edges. Um, V sub I1, V sub I2, V sub I2, V sub I3, all the way to sort of V sub IN minus 1, V sub IN, where what you're doing is you're just going from um, one vertex to the other, right? So really, this is just a more formal way of writing the fact that you're going from V sub I1 to V sub I2 to V sub I3, and so on, right? So this is a walk, okay? And in a walk, you can um, go through the same edge as many times as you want, and you can go through the same vertex as many times as you want. So what do I mean by that? Let's say I have a graph like this, okay? Then a valid walk could be I start here, I go here, I go here, I go here, I go here, and now I go back here, I go back here, I go back here, and I go here. Okay, so that's a valid walk, right? You can repeat, you can go through the same edge many times, and you can go through the same vertex many times. Okay, and so that's a walk. Then a path is just a walk in which no edge is repeated. So if I go back to this example here, I had done my walk. So let's draw my walk. So my walk looked like I go here, then here, then here, then here, and then I do the same thing twice, right? So I do this, this, and then this. Okay, so that's a walk, right? But that's not a path, right? Because in a path, you can't repeat the same edge more than once. So a path would have been if I just um, went through this set of three edges only once. So then a path would have been, you know, I start here, I go here, 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 and here. So that's a path. And then I have an even greater restriction, a simple path. So a simple path is a path in which no vertex is repeated. So basically, a simple path is I can't repeat any edges and I can't repeat any vertices. So for this path here, I can't even do this kind of a loop here because uh, however way I do this loop, I'm going to go through this vertex more than once, right? So a simple path, let's say if we want to name or label our vertices, let's say this is A and B. A simple path from A to B would just be you go from A to this intermediate node C, then you don't go through this loop here. Whoops, you don't go through this loop, and then you go to B, right? So that would have been the simple path. It would have been A to C, C to B. So this would have been the simple path. Okay, and I have another example here of a simple path. This is from the graph GA from a few slides ago. The simple path from 1 to 4 would have been, I start at 1, or a simple path would have been I start at 1, then I go to 2, then I go to 3, then I go to 4. But if I had done something like, let's see, if I had done something like I go to 1 to 5, then 5 to 2, then 2 to 1, and then 1 to 4, then that's not a simple path anymore, right? Because I just repeated the vertex 1 twice. Okay? Okay, and that's how, those are different terminologies of walking through a graph, which is going to be important when we more formally talk about um, these graphs as computational machines. So I know that doesn't mean anything to you right now, but it will in a few videos from now. Okay, the other important thing to know is ways of looping through a graph. So what I mean by looping is starting a walk and ending. So starting a walk vertex vi and ending it at vi. That's what I mean by a loop. So you start something at one vertex and you come back to the same vertex. So one easy way you could do that is if you have a self loop. So a self loop is, for instance, if you have, let's say you have this edge A here, if you have a self loop, right, then a way to start at A and end at A is just taking your self loop from A back to A. So that's one way. And that's more of a special case than anything. Then a circuit, okay, a circuit with a circuit with base Vi is how you sort of say it formally, is a walk that starts at Vi, right? So it starts at Vi and it ends at Vi. So that's a circuit with base Vi. So it's a walk, so you can repeat any number of edges and any number of vertices that starts at Vi and ends at Vi, right? So if I draw another example graph here, right? So if I want my if I want to start at, let's say, V1 and end at V1, what I could do, right? What I could do is I could start at V1, then go here, 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 and here. Okay? And actually, I'm not even repeating edges, I'm just repeating a vertex, but this still counts as a circuit, right? But a circuit with no repeated edges is called a cycle. And that was actually a cycle, right? So if I went from V1 to here, 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 I'm not repeating any edges. I'm just repeating this vertex here, right? And so that counts as a cycle. However, it's not a simple cycle because a simple cycle is a cycle in which no vertices other than the starting vertex are repeated. Okay, so that means that if I have the same cycle as before, this doesn't count as a simple cycle because this vertex is repeated more than once and it's not the base vertex, right? So a potential simple cycle for this this graph and starting at V1 would be I start at V1, then I go here, here, and here, right? Because in this case, I don't repeat any edges and I don't repeat any vertices other than the starting vertex, okay? So this was for like an undirected graph, but you can also do the same thing for a directed graph, right? So here, a simple cycle with base A could be you start at A, then you go to D, then you go to C, and then you go to A, right? So that's a potential simple cycle for this graph. Okay, and lastly, I also want to talk about a very special type of graph, which is known as a tree. But to talk about trees, I first have to define an additional concept, which is the concept of connectedness. So if you're given a graph G, which we now know can be represented formally as a tuple of vertices and edges, we say that that graph is connected if and only if for every pair of vertices, so for every u comma v in V, there exists or there is a path from U to V, right? So for every two vertices UV, there exists a path from U to V, right? So that's what it means for a graph to be connected. So basically, it just means that there aren't any separations, so there aren't any clusters of graphs, right? At least that's what it means for an undirected graph. So for instance, this graph here, right, this graph is clearly connected because take any two vertices, let's say this one and this one, there exists a path from here to here, right? So connected just means that there isn't something like this, right? Where I have like two islands. And so clearly there isn't a path from this vertex to this vertex because I can't do this and like jump magically to here, right? That's impossible. So that's what it means, at least for a an undirected graph. And so here in trees, I'm actually just going to be talking about undirected trees until I get to a more specific rooted tree version. So now that we know the definition of connectedness, we can define what a tree is. So a tree is a connected graph that is acyclic. So what does acyclic means? It means that it contains no cycles. No cycles. So if I go back to like this example here, this graph, so this graph, let's say GC, it is connected, right? So it's connected. But is it acyclic? Is it acyclic? Question mark. Well, no, right? Because I can see that there's already a few cycles. So there's maybe this cycle here, there's this cycle here, and there's this cycle here. But if I remove this edge, right, and I remove this edge, now I have a tree, right? Because I have no way of creating a cycle. So I go here, I can't create a cycle, I can't create a cycle, can't create a cycle. So now it's acyclic. And so now GC is actually a tree. Excellent. And a forest is a not necessarily connected acyclic graph. So really, a forest is just a collection of trees. So let's say I have a tree here, and then I have a tree, say, here, and another one here. Then, you know, this is a tree, this is a tree, this is a tree, and then all together, this is a forest. Okay. Very good. Okay, and another example here. So if I had, so remember my graph GA. So this was my graph GA, and I had a few cycles in my graph GA. So what I did is, if I removed, let's say, this edge and this edge, then I would have gotten a tree because I would have gotten rid of all my cycles and I would have created just a tree. Okay, so that's this example here. This example here. Okay, and finally, I'm just going to erase this because I need place for an example. Finally, a rooted tree. So a rooted tree is a directed tree that has, so first of all, what does a directed tree look like? So a directed tree could look like, say, something like this, right? So you have something here, something here, let's say, right? And so that's clear that there isn't a cycle here. So there's a vertex like this. Okay, so that's a directed tree. Now, a rooted tree is a very special type of directed tree that has um, a vertex called a root, the root. Okay, so I corrected myself. It's not a root because a rooted tree has only a single root. So it's the root of the tree. And so the root of the tree, um, the root of a directed tree is the single vertex that has no uh, incoming vertices and only has outgoing vertices. Okay, so what does that look like? So in this case here, I actually already have a rooted tree because this is actually my root because it has no incoming vertices, but it has outgoing vertices, right? So this is definitely not the root, this is not the root, this is not the root. These have incoming vertices but no outgoing vertices, so these are actually the leaves of my rooted tree. These are the leaves. So I guess I should just written leaf. So that's a leaf, and then that's a leaf. Okay, and this is the root of my tree. Okay, so typically this is seen in graph theory. You know, you define a few more concepts like, you know, you have the parent and the child. So the parent, eh, for instance, a pair of parent children here could be, you know, this edge here because it's above or because it has an edge outgoing and ingoing into this edge, then this is the parent and this is the child. Then if you sort of think of this sort of genetic structure or sort of uh, generational structure even more, then this could be the ancestor of these two guys and this guy, right? So you have a few more definitions like that, but really, for the purposes of this topic, you really only need to know about rooted trees, um, what they really uh, what they mean as a mathematical object, and sort of the hierarchy sort of comes naturally, I think. Um, okay, so I think that's all I wanted to say about graph theory. The next thing we'll talk about is a review of some proof techniques that you'll be using throughout these tutorial videos. All right, see you next time.